In this video, we will discuss interest rates and compounding periods. We will start with the example of an interest rate of 10%, a present value of $1,000, and we will look at just a one-year time period. And then we're going to look at how much this $1,000 will grow at 10% over that 1 year, depending on whether the compounding period M is once a year, twice a year, 4 times a year, monthly, 360 times a year, 365 times a year, 1,000, 10,000, 100,000 are basically an infinite number of times a year. Well, the first case is easy. It's just going to equal 1,000 times our rate of 10%, which is going to be 1 plus B3, and that's going to equal $1,100. In our second case, we get compounding twice a year, which means after the end of the first 6 months, you get $1,050, or your 1,000 times 10% divided by 2, or 1.05. And during the second half a year, you get the other 5%. So I get 1,050 times 1.05 equals $1,102.50. So this compounding twice a year increases the future value at the end of the year by $2.50. That extra $2.50 is interest that we earned on the $50 interest in the first place. And what we will see is the higher the number of compounding periods, the more interest you earn on the interest. So for 4 times a year, after the first fourth of the year are 3 months, you're going to have $1,025. And then during the second fourth of the year, you will earn 1.025% times that. And then the same thing in the third quarter and the fourth quarter, giving you at the end of the year, if compounding takes place 4 times a year, $1,103.81. Again, slightly more for 4 times a year than 2 times a year. If we go up to 12, again, we get a little bit more. And then gradually, as we get up to 360 are daily during the year, it converges to $1,105.16. And you get another penny if we go all the way up to 100,000 times a year, are basically infinity. So compounding with an infinite number of times a year, we use a different formula. So the formula for compounding 1, 2, 4 times a year is future value is present value times 1 plus I, the interest rate, divided by M, the number of compounding periods, all to the MT, where T is the number of years. Well, under the conditions that M here goes to infinity, then you can do a Taylor series of this equation and a Taylor series of this equation, and you find that they are the same. So if the number of compounding periods M's goes to infinity, this equation goes to future value equals present value exponent of RT, where exponent, or e to the RT, is 2.71828 to the RT. So again, more compounding, more interest on the interest, and we get a higher future value at the end of the year. We can also do calculations on showing how to convert from one type of interest to another type of interest. To some extent, this is the same thing as converting from the metric system to the English system. You can have the same interest rate just measured in different ways. And to show that that's the case, we will now use an example of the interest rate equaling 8%. And we're going to set this equation equal to this equation, and then we're going to rearrange and solve for R, the continuing compounding rate, where I is sort of the quantized rate. So if I whack off the PVs on both sides, I'm going to end up with 1 plus I over M to the MT equals exponent to the RT. We can also take it to the 1 over tth power and it'll eliminate the t on both sides. And then you would solve for r by taking the inverse of exponent, which is natural log, and we're going to end up with m, natural log of 1 plus I divided by m. Again, we will look at the different compounding periods m going from 1, 2, 4, etc. So these are our compounding periods m. And we'll have m equals 1, 2, 4, 12, 360. Well, for m equals 1 and I equals 0.08%, the equivalent continuous compounding rate is 0.07696. So again, since it's continuously compounding, it's going to be less than the quantized compounding once a year of 8, since for the continuous compounding you will earn interest on the interest. If we go twice a year, then this number is going to get slightly higher to 0.07848. So all we're doing is using this equation here. We can click on it and show that. So m is going to be our E10 here, and then we're going to have natural log of 1 plus I, our interest rate here, which is G3, then divided by E10, which is again going to be our m here. And as we gradually increase m, again our interest rate r goes from being slightly below 0.08, gradually converting up to basically 0.08 as m goes to a very large number. So that is looking at this equation and solving for r. We can also look at this equation and instead solve for I. So we'll now use the example of r continuous compounding as 0.05, and we will now solve for I, the quantized compounding rate. So how do we do that? We again start with this equation, or we can take it on to this equation. We take both sides to the 1 over t, and then you subtract 1 from both sides, and I end up with I over m equals exponent r over m minus 1. And then I'll multiply both sides by m, and I end up with I equals m times exponent r over m minus 1. And now we do the same sort of calculation, starting with m, the number of compounding periods, 1, and going up to infinity. And our continuous rate is now 0.05. The quantized rate that is equivalent is going to be greater than that, because for a continuous rate, you're going to get more interest on the interest. So we start out here first with m equals 1, and we put 1 in here, and 0.05 in for r, and we get 0.0512. Then the next one, we stick in 2 for m, r is still 0.05, and we end up with 0.050630. And once again, as m increases, gradually now this I will go down to 0.05. As you get to a very large m, 100,000, it's basically 0.05, and we take it out to infinity. As m goes to infinity, then I goes to 0.05. I thank you for watching this video.